I got a bottle of Patron and some lights off, 2 red devil looking eyeballs, and I finna turn up when the night falls. If you hear a siren, then it's my fault. Jump in my whip, baby, let's ride. We ain't gonna stop at a red light, and I'ma take shots like a Tech 9. It's gonna get live. Here we go, it's about to go down. Let me know, I'ma buy another round. Get low, drop it down to the ground. Oh yeah, wow, shorty make it bounce. Mama see the put cuffs on my cardiac. Took my breath away like a heart attack. And I'ma spend every dime and my money back. Everybody wanna know. If you're ready, let me know. Let's go. If you're ready, let me know. Let me know. Let me know. If you're ready, let me know. Here we go. Let's go. I got a bottle of Grey Goose and ice cubes. Type of drink that'll put me in the right mood. 80 proof's gonna lower my IQ. And I've been the same way since high school. I look shorty right in her brown eyes. She about to take a trip to Cloud 9. I'm the man, baby, I get the crowd hype. I turn the cadence of a hook into a soundbite. Here we go, it's about to go down. Let me know, I'ma buy another round. Get low, drop it down to the ground. Oh yeah, wow, shorty make it bounce. Mama see the put cuffs on my cardiac. Took my breath away like a heart attack. And I'ma spend every dime and my money back. Everybody wanna know. I got the juice like a snow cone. Ice in my veins and a cold flow. I'm getting cash overseas by the boatload. You wanna ride my wave? That's a no-go. Senoritas going loco. Make it bounce like a pogo. All my haters see rojo. They big mad cause they coming up short like Frodo. Activate the beast mode. I keep it hot, give your brain a heat stroke. You ain't a big shot, you some basic B-roll. The world is mine like my name's Pacino. Hey, it's Nico, I guess I'm back. Catch me in the fast lane on the right track. And my shorty is a 10 like a dime bag. Got me feeling like a milli, check the price tag.
Got the party jumping like crisscross. Got the gold chain and the wristwatch. Pull up on the scene like a big shot. EDM and hip hop, ain't no time for piss stops.
Got the party jumping like crisscross. Got the gold chain and the wristwatch. Pull up on the scene like a big shot. EDM and hip hop, it's my style.
No time for daydreams. All my brothers get money, we call it gangrene. Just another day, but I focus still on the same thing. Us against everyone else, I recommend you change teams. Who the hottest in the city? We the top 2. You said your music was litty, but that is not true. Just being honest, you should really just stop, fool. Matter of fact, empty no pockets, give me that watch too. My mind is wicked, that's why I spit it so hostile. Freaky girls in the crib, it's like I live in a brothel. All I spit is Leviticus, but I'm not an apostle. My nuts hang low, long and they're colossal. Black trader black, she messiah to the misfits. Run circles, run these rappers till my shit splits. You a little late to the party, baby, I been lit. If you ain't on the friend list, you better mind your business. Got the party jumping like crisscross. Got the gold chain and the wristwatch. Pull up on the scene like a big shot. EDM and hip hop, ain't no time for piss stops.
Got the party jumping like crisscross. Got the gold chain and the wristwatch. Pull up on the scene like a big shot. EDM and hip hop, it's my style. Gets everything that she wants in abundance. Knows how to be a lady in public, but she can get crazy. Ooh, I love it. She got a lot of weight in her luggage, and shorty ain't bluffing. She might snap on you like it's nothing. Everything I thought I knew is redundant.
Explosive temper, I hear smoke detectors. If I don't surrender, she might hold a lecture.
Every apology's a token gesture. I'm sorry, baby, I don't know no better. You get mad when I show no effort and turn the summer into a cold December. Cruise on the high road, dodging the potholes, tied up and I'm blindfold. She got me going psycho. I walk on a tightrope, my feet getting ice cold, my head spinning like a cyclone. She got me going psycho. I got CBD, now we should kick back, pop in a DVD, yeah. Hold up, baby, we should keep the peace before one of us blows up like TNT. Let's go. I guess I'm crazy too, not right in my mind, but I play it cool. A lot of emotions I convey are cruel, and my toxic traits are like deja vu. Ooh, that's the way I do, I'm a hot mess. Face the truth, I don't mean everything I say to you, but I know that I got you going crazy too. Damn. Cruise on the high road, dodging the potholes, tied up and I'm blindfold. She got me going psycho. I walk on a tightrope, my feet getting ice cold, my head spinning like a cyclone. She got me going psycho.
Alive can't put me in a box. I redefine any definition you got. I am the tiger, I'm making steps to the top. The flames, I whip it up, you just gotta hand me the rock. Take a seat, you cannot stand it. All I know, the flow harder than a Scotch bonnet. Don't try studying me, you cannot manage. This ain't what you want, bitch, I'm a fucking phenomenon. This ain't what you want, bitch, I'm a fucking phenomenon.
Yeah, you better listen. I'm bringing heat, you'll be a fan when I start rapping the way I'll have your fucking head spinning. I'm known as spit vicious, release bombs and go tick tick. Boom, you blow me, that head missing. I'm a phenomenon, stacking cheese like it's Parmesan. 8 different flows, call me Octomom. I'm moving fast like the Autobahn, and I'm independent, so I'm not your fucking starving like it's Ramadan. Sick, twisted, gifted, can't copy, printed, can't hold me down. I shape shift, I'm liquid. I killed this beat, I might get convicted. They know how I move, it was predicted. Persistent, spoke it into existence, so consistent, no assistance. Hear me once, become addicted. If I rap it, then I live it. There's no cap when I be spitting.
This ain't what you want, bitch, I'm a fucking phenomenon. This ain't what you want, bitch, I'm a fucking phenomenon. sound. Call the corner up, no needed medical. Twin 9 millies identical. Goons in the back, God send them through. One phone call, got the squad coming soon.
I be strapped up with the top down. 100 round stick making drum sounds. Got 'em like, what? Playing dumb now. Gotta mask up cause it's up now.
Gotta mask up cause it's up now. 100 round stick making drum sounds. Stay strapped up with the top down. Drop 'em on beat, going dumb now. Yeah. Yeah, I ain't never seen a hitter like this before. Hit the floor before your ass hit Whitney notes. Turn them into singers, working out my index finger. Crash them at the traffic light, then I'ma hit the blinkers. Headshot, no brainer, that's a quick thinker. If you on some gangsta shit, then I'ma link with you. I'm the captain of the boat, but I sink hitters. Cameras flash and just smile for your last picture. Catch me sipping on that gas out of glass pitcher. Turned up, better hope you got your mask with you. Hit man, get him checked off the task quicker. 6'4" strapped up, ready to roll with you.
I be strapped up with the top down. 100 round stick making drum sounds. Got 'em like, what? Playing dumb now. Gotta mask up cause it's up now.
Gotta mask up cause it's up now. 100 round stick making drum sounds. Stay strapped up with the top down. Drop 'em on beat, going dumb now. Yeah.
My skin is pale, but I'm a black sheep. Riding through the city, Satan in the backseat. Hey yo, that's me, I run it like a track meet. A rap fiend, I set the bar high like an athlete. Step in the booth and Zach gon' drop that 808. Cause the vibe is dope and the beat is cracking, now it's getting laced. I'm sharp as a razor blade, I can blow your mind like JFK. I do what I want, you ain't gonna box me in like David Blaine. We get it poppin', homie, day and night. Got the party jumping, about to break the ice. Stay up on my grind, that's my way of life. I got tunnel vision, I'ma chase that ray of light. And when a Filipina tells me Malakita, I put two and two together like a ballerina. This music is more than a paycheck, no money in the bank cause I make sense. I put in work till I'm brain dead. I spit a fast zone like a break next, and the crowd goes wild, mayhem. We get it poppin', homie, day and night. Got the party jumping, about to break the ice. Stay up on my grind, that's my way of life. I got tunnel vision, I'ma chase that ray of light. Gotta keep the party rocking. The vibe is dope, the Let me know, I'ma buy another round. Get low, drop it down to the ground. Oh yeah, wow, shorty make it bounce. Mama see the put cuffs on my cardiac. Took my breath away like a heart attack. And I'ma spend every dime in my money back. Everybody wanna know. If you're ready, let me know. Let's go. If you're ready, let me know. Let me know. Let me know. If you're ready, let me know. Here we go. Let's go. I got a bottle of Grey Goose and ice cubes. Have a drink that'll put me in the right mood. 80 proof's gonna lower my IQ. And I've been the same way since high school. I look shorty right in her brown eyes. She about to take a trip to Cloud 9. I'm the man, baby, I get the crowd hype. I turn the cadence of a hook into a soundbite. Here we go, it's about to go down. Let me know, I'ma buy another round. Get low, drop it down to the ground. Oh yeah, wow, shorty make it bounce. Mama see the put cuffs on my cardiac. Took my breath away like a heart attack. And I'ma spend every dime in my money back. Everybody wanna know. I got the juice like a snow cone. Ice in my veins and a cold flow. I'm getting cash overseas by the boatload. You wanna ride my wave? That's a no-go. Senoritas going loco. Make it bounce like a pogo. All my haters see rojo. They big mad cause they coming up short like Frodo. Activate the beast mode. I keep it hot, give your brain a heat stroke. You ain't a big shot, you some basic B-roll. The world is mine like my name's Pacino. Hey, it's Nico, I guess I'm back. Catch me in the fast lane on the right track. And my shorty is a 10 like a dime bag. Got me feeling like a milli, check the price tag.
Got the party jumping like crisscross. Got the gold chain and the wristwatch. Pull up on the scene like a big shot. EDM and hip hop, ain't no time for pit stops.
Got the party jumping like crisscross. Got the gold chain and the wristwatch. Pull up on the scene like a big shot. EDM and hip hop, cause my style.
No time for daydreams. All my brothers get money, we call it gangrene. Just another day, but our focus still on the same thing. Us against everyone else, I recommend you change teams. Who the hottest in the city? We the top two. You said your music was litty, but that is not true. Just being honest, you should really just stop, fool. Matter of fact, empty no pockets, give me that watch too. My mind is wicked, that's why I spit it so hostile. Freaky girls in the crib, it's like I live in a brothel. All I spit is Leviticus, but I'm not an apostle. My nuts hang low, long and they colossal. Black trader black, she messiah to the misfits. Run circles, run these rappers till my shit splits. You a little late to the party, baby, I been lit. If you ain't on the friend list, you better mind your business. Got the party jumping like crisscross. Got the gold chain and the wristwatch. Pull up on the scene like a big shot. EDM and hip hop, ain't no time for pit stops.
Got the party jumping like crisscross. Got the gold chain and the wristwatch. Pull up on the scene like a big shot. EDM and hip hop, cause my style. 10, she 100. Gets everything that she wants in abundance. Knows how to be a lady in public, but she can get crazy. Ooh, I love it. She got a lot of weight in her luggage, and shorty ain't bluffing. She might snap on you like it's nothing. Everything I thought I knew is redundant.
Explosive temper, I hear smoke detectors. If I don't surrender, she might hold a lecture.
Every apology's a token gesture. I'm sorry, baby, I don't know no better. You get mad when I show no effort and turn the summer into a cold December. Cruise on the high road, dodging the potholes, tied up and I'm blindfold. She got me going psycho. I walk on a tightrope, my feet getting ice cold, my head spinning like a cyclone. She got me going psycho. I got CBD, now we should kick back, pop in a DVD, yeah. Hold up, baby, we should keep the peace before one of us blows up like TNT. Let's go. I guess I'm crazy too, not right in my mind, but I play it cool. A lot of emotions I convey are cruel, and my toxic traits are like deja vu. Ooh, that's the way I do, I'm a hot mess. Face the truth, I don't mean everything I say to you, but I know that I got you going crazy too. Damn. Cruise on the high road, dodging the potholes, tied up and I'm blindfold. She got me going psycho. I walk on a tightrope, my feet getting ice cold, my head spinning like a cyclone. She got me going psycho.
Okay, I think my screen and video are completely audible and visible. Okay. Okay, let's just start the topic. I'm Yug Sharma from IIT BHU, and the session of this agenda will be just trying to understand what segmentary beats are. So there are of course some prerequisites for this, which are you should have a decent understanding about standard segmentaries and also lazy propagation. So I'll be discussing about them in brief if you haven't revised them, but without them it will be quite tedious to directly look at segmentary beats and problems and proofs based on them. So yeah, just let's get into this after I confirm everything. Okay. Yeah. So let's just start with our basic segmentary. So I'll be just discussing the some queries for uniformity and just try to keep this lecture as basic and as fundamental as possible. So our problem statement will be like something like we have an array of integers of size, let's say n, and we'll be having q queries, and for each query, like there will be two type of queries. In first type of query, we'll be trying to update an element based on its index. Let's say we have index I, and that element will now become equal to x, so ai will be equal to x. And second query will be of the form l comma r, and for each second query we'll have to output the sum of all elements from l to r. So like, it's the standard segment tree. We'll build a segment tree here. Let's say there are 8 elements, so this will contain the sum of elements indexed from 1 to 8. This node will contain the sum of elements indexed from 1 to 4 and 5 to 8 and so on. Okay, just wait a second. Okay, sorry for the interruption. Okay. Yeah, like these nodes will be containing the sum of elements from 1 to 2 and just so on. These single nodes will carry just the single elements. This will be how our segment tree will actually be looking. So like this is just for visualization purpose. Actually it will be something like this. And just all nodes connected to them. Okay. Now let's say we are changing some element, let's say element 3. Element 3 is getting updated to some value x. So now what we'll do is we start our propagation from the root node of the tree, and we'll check the L and R values, and whenever we get our required value we'll stop there. Like for example, we will traverse the entire tree. We change the color once. We'll traverse the entire tree from here to here, and we get our required index 3. And now I'll just update this element, and while traversing back to the root we'll take this new element and this already existing element and update this sum. Now this node is updated, and we already had this node. Now these two will update this node. So like this will take log n time for each query, since the height of this entire tree is log n. So our entire time complexity will look something like q of log n, since there are q queries and log n is the height of the tree. So yeah, this was pretty much it for our basic segment tree. Now lazy propagation will be a bit more tedious than this, but it will be slightly closer to the idea of segment tree beats. So I'll take some time discussing it. Like lazy propagation. The main difference between lazy propagation and segment tree, like the standard problem that we are solving is, in segment tree we are updating a single element, and then our sum query is just asking for the sum of all the elements in that range. But in lazy propagation we are not just updating a single element, we are updating a range of elements L to R. For example, there is an array of size like 1, 2, 3, like size 7, and all the elements from 3 to index 6 are changed to some value, let's say 4. Or we can even solve something like all the values are increased by 4. So this is the kind of problem that we can solve using lazy propagation. Let's just take a basic overview of how it actually works. So yeah, let's take 8 for uniformity of the segment tree again. Again we are storing the exact same thing, like this will contain the sum of elements from 1 to 8 and so on, but we'll have to store one more thing, and that will be a tag. I think I have to take an example for this. Let's just take this example of 1, 3, 4, 7, 3, 2 and 3. Okay. Now our topmost node will contain the sum of all these elements. That will be 24. Okay, 24. The next node will contain the sum of first 4 elements 15. Next node will contain the sum of last 4 elements, which will be 9. Similarly here 4, 11, 5 and 4, and then these are the single elements. Now let's just say we are updating all the elements from range 4 to 7 or 4 to 6. Yeah, 4 to 6 to some value, let's say 4. Now what we'll do is, here we have index 1 to 8. There will be two conditions basically, our break condition and tag condition. In segment tree above, we were not including this tag condition. We were breaking when our required range L comma R, for which we are querying this entire tree, not the entire tree but whatever node we are traversing. Whenever this value L comma R is completely out of the range of that node, we'll just break and do not further continue in that direction. But here our break condition still remains the same, but rather than the condition where our range is completely indulged in this range. For example, let's say this range L1 to R1, if this is completely a part of this range L to R, basically L1 is greater than L or equal to L and R1 is less than or equal to R, then this will be our tag condition. In regular segment tree, we are just making this change, but here we'll be updating the entire value. Now how will this proceed? Basically, we are updating all the values from 4 to 6. Yeah, 4 to 6 to 4. Now we'll start traversing the tree. 1 to 8 is still overlapping with 4 to 6. So we'll just traverse its node and go in both the directions. Now here, the range is 1 to 4. It's still overlapping with 4 to 6. So we'll further go down in these two directions. Now here the range is 1 to 2 and here the range is 3 to 4. This is completely out of the range that we are looking for, so we'll just stop it and do not do anything. Like 2 to 4 is still in this range, so we'll further go down. Further go down in these two directions. Here we have 3 to 3 and 4 to 4. Again, this one is completely out of the range that we are looking for, and we'll now update this element. This element will be updated to 4, and this is not a tag condition, we are just still updating a single element. So tag condition is basically propagating the change that we are making here to the children of the node. So since this child, this is a leaf node with no children, so we'll just stop it here. So either a leaf node with values ranging in the range that we are looking for, or a range that is completely out of the range that we are looking for. Okay, now we'll go up and update just like we were doing before in a standard segment tree. Now let's try to look in this direction. Here the range of elements is 5 to 8. It's still overlapping with 4 to 6. Here the range of elements is 6 to 7. Here the range of elements is 5 to 6. Sorry, it will be 7 to 8. So 7 to 8 is completely out of what we are looking for, and 5 to 6 exactly fits in this range. So we have to update this 5. Now each element is becoming 4, and there are 2 elements in this range. So the initial sum of these elements is 5, and now what will be the sum? There are 2 elements and both of them are becoming equal to 4, so it will be 8. Like we can easily calculate it. Just the number of elements into the element text that we are changing each element to, which will give our new node. So we'll update this 5 to 8. We'll just update this 5 to 8, and now here will the tag condition come in. We'll put a tag on this and this node. Like, we are not putting another integer, we are just assigning a tag for each of the node. Initially all the tag values are zeros. Basically we are just building another segment tree like structure. So the tag for this will be 4, since the values of this node have been updated by 4. So we are propagating the same change to all the nodes that were below this, because ultimately they are the same range, right? Like, if this is a parent, so each of its children are just a sub part of this. So if there is a change in the parent, that change will propagate down. So like, we'll not change this now, but whenever we visit this again, then before doing any operation on this node, we'll just check once if there is a tag present or not. So if there is a tag present, we'll do the same exact change and then perform our required operation. And one thing to keep in mind is, if it still had more children, then after changing this node's current value, we'll also have to propagate this tag value to its children further down, and this tag value will become 0 and the tag will propagate down. So we are basically delaying the update query, but the correctness is still kind of there, because we are just changing the time of update, but ultimately we are getting to the correct answer. So that's where the name lazy propagation comes from. So I think this should be more than enough for a brief overview of lazy propagation. Or we can just try run it on another example. Let's say, what could be a good example? Let's just delete everything right now. Yeah, it's more than enough. Let's say we are changing this. Let's say we are changing this entire range. So we'll just have to traverse down here at this node. Yeah. And we are updating its value to 4. Now I'm ignoring the updates that we did in the previous example, but so what will this 9 become? Will this be 4 times 4, which will give us 16. So this value will be changed to 16. And also we have to keep in mind that its children's tag value will be updated. So this will be updated to 4 and this will be updated to 4. Now after we have updated this tag value, we'll just move to the next query. Obviously it's kind of obvious, before moving to the next query we have to propagate back to the root node and just do the updates there, but we are trying to avoid going down there. So the time complexity is pretty much similar to what we saw in standard segment tree. So yeah, the tag value of these nodes have been updated. Now if we again try to run some query like 3 to, let's say, we'll go down here, we'll come here, and before making any changes on this node, we'll see there's a tag value present, and we'll just update it 2 into 4 and 8. This will become 8. The tag value will propagate down 4 and 4, and then we'll do our necessary update. Let's say we need to update this to 5, then this tag value will become like it became 0, and now it will become 5 because we are updating it to 10. And yeah, that will also update the children's tag values, so it will become 5 as well. Yeah, so like in this problem statement, we are just updating a range of elements to some single value x. So a tag might be able to overwrite the another tag. Like initially, if tag values are -1, that then it basically means that we don't have to update, like there is no tag present on that node. But if x is non-zero, then we have to update it. And let's say this already had a tag 6 and this already had a tag 6 as well, and through its parent it will try to get a new tag 5 because the parent is now updated to 5. So this 6 will be overwritten by 5, which is pretty logical as well, because we are changing a value, we are not trying to increase a value. Let's say if the problem statement was increase the range by 5, each elements in the range by 5, then after updating the elements of a particular node, we have to propagate 5 to its children. But we don't have to override this tag value now. We have to add to this tag value, because now let's say something like add 6 to the current updated segment tree or the updated array, whatever. We have to add 6. Then this tag value will become 5 plus 6 and not just 6, because we are updating it twice, right? So in this case we were overriding it, but logically it kind of follows we are not overriding this time. We'll just have to keep on adding the tag values. Okay. Now let's just move on to the main agenda of this session, segment tree beats. So yeah, like the lazy propagation name I think was pretty logical for this topic. Like we are not lazily propagating, but we are kind of delaying the updates, so the name lazy propagation seems kind of logical. But if you're wondering where this beats come from, so yeah, it's basically an anime called Angel Beats. Yeah, that's more or less the reason why it's called segment tree beats. Like, not my fault. So what can we actually do in segment tree beats? One thing you might have noticed is that here in lazy propagation and even in the standard segment tree, there was a break condition as a common condition, right? And this break condition only depended on the indices that we had, like L to R. We were just checking if let's say the indices of any node are LL and RL in the segment tree, and L and R are the nodes that we are looking for. Then we are just checking if L and LL, whatever the relation is between them, greater than or less than equal to, and RR. And yeah, that was pretty much it. And based on this, we were propagating the entire tree, not the entire tree again, but yeah, you get what I'm trying to say. So the break condition and the tag condition only depended on these values. But in segment tree beats, it's a little complex. Like these conditions will also depend on the values that we are looking for, like what values are present in that range. Those will also try to determine whether we have to propagate further, or we have to add a tag, or we'll just have to break. And using these different conditions, we'll try to bring the time complexity of certain problems that would be too difficult to solve using lazy propagation. Like just lazy propagation. It's a slightly advanced version of it, but the idea is completely different. So yeah, we'll just try to bring their time complexity for average time complexity for all the queries down to logarithmic rather than linear. So let's look at a problem statement, something like again we have an array of 1, 2, 3, 4, 5, 6, 7, 8 integers, and again we have two types of queries. The first type of query will contain let's just look at the second query first. Again we will be having the sum query. We have to output the sum of all the elements from L to R. Now this first type of query is the update query, and what are we updating? We'll be updating all the elements from L to R by element mod x, where x is any integer. Basically AI will become AI mod x for all I in range L to R, including L to R. Now this first you need to understand why we have to rely on another concept for this problem statement. We'll try to understand the idea of segmentary beats using this problem statement, and just look at another problem statement after it and try to prove why they are working and not we cannot solve them using lazy segmentary, and then analyze their time complexity. So yeah, why cannot we solve this using lazy segmentary? A lazy segmentary, I should not say lazy segmentary, okay, lazy propagation. We cannot just use lazy propagation. Like for lazy propagation, what we were doing, a single node contains the value of sum for all the elements in this range, and the problem statements that we were able to solve using this were basically assigning all the elements in this range to some value x, or increment or decrement all the elements in this range by some value y. This can easily be written or updated using a very basic mathematical equation or expression. Like if we are updating all the elements to x, whose sum we already know, then the sum will just be updated to number of elements times x, and this will become a new node, and we'll just propagate this value down, and those values will just be changed after it in the same way. And if we have ai plus y for all elements, then the new node will just become sum plus number of elements time y, and again we are able to propagate this downwards, since the same pattern will keep on repeating. But if we have something like ai mod x, mod is equals to x for each update, then we cannot predict anything. Like if there are 8 elements whose sum we already know, we definitely cannot predict it directly what will the sum of all the elements taken mod x individually will return. And again, since we cannot predict it, we cannot even propagate it down. Like if we calculated the sum, let's say we went to all the nodes and calculated the sum, even then we cannot just propagate down to its children and just write x and update it in over one time. we'll have to propagate everything. This cannot be solved using a standard lazy propagation. We'll need some different concept for it. I think this should be enough. Or let's discuss another problem statement, like something like AI is equals to min of x comma AI. Again, we are updating all the elements in the range L to R to minimum of that element and x. Again, we'll not be able to predict the sum. If, for example, we have elements 1, 3, 4, 7, 6, and we are updating each element to min of 5 comma AI, then we cannot directly predict it in one time by just traversing. Like in constant time, we cannot predict what will be the sum of it after we update it in this way. We'll have to traverse it entirely, and that will just lead to a very, very bad time complexity. So, yeah, let's just start with our idea of segmentary beats. It's just, we'll be starting with this problem statement. This is much simpler, or decently simpler than this one. They're related to each other, but the AI mod X problem statement would be better for intuition building at first. So, okay. Again, we have a segmentary. Each node will obviously carry some values, sum of all values in those range. But we'll have to store some extra information to solve this problem. Like, it might not be so intuitive to just write them, but okay. We'll have to store some extra information regarding this. We'll have to keep track of the maximum element present for each node. Like, like in this example, if 1, 3, 4, 7, the maximum value is 7, we'll have to store this value 7. Also, now what can we try to build from here? If we have a range L to R and we have to update each element as AI mod X. Okay. And we are storing some extra information. We already have the sum, which is pretty much useless for update, but yeah, we have it. And we also have the max element. There will be two cases. Our value X. In case 1, let's name our max element M or M naught. Our max value X is greater than M naught. And second case will be when it's less than or equal to M naught. Okay. Now we can easily notice it in this case. If X is greater than M naught, then X is basically greater than all the elements present in that node, right? So there will be no change in that node, and no change in the children or further children of that node as well, because they are ultimately covering the same range. So we can just stop propagating further, and this will be one of our break conditions. Also, we are I'm assuming it's pretty clear that our break condition using the indices are they're pretty clear, I guess. Like R should be less than L, or RR should be less than L, where RR is LL comma RR is the range of a node in segment tree. Either this or L should be greater than LL. No, LL should be greater than R. Like these two are the break conditions that we have from a standard segment tree, and this is the break condition that we have added here. So yeah, if X is greater than all the elements in our range, then we won't have any update. We can just stop propagating further. Here, if we have X smaller than M0, if we have X smaller than M0, we have to propagate to both the children. Like if in a range, let's say the max, let's say the sum is S and the max element is 8 and the value of X is 4. So we cannot predict anything. Like there can be any elements in this range, like 1, 2, 3 and 8. Yeah, only 8 will be changed here. But there can also be something like 5, 6, 7 and 8. All the elements will be changed here. So we have to propagate down to both the children. And we'll propagate down until we get this condition X greater than M0. Either this condition or we hit a leaf node. We hit a leaf node which is in a valid range, of course. So for updating an element, we have to propagate down to the leaf node, to the exact index. The time complexity of this might sound like it will go linear per query, but we'll prove it later. That let's just try run on an example using this approach. Again, I'll be taking something like 1, 3. Let's just take some big numbers for mod, and then just 6, 4, 3. How many elements are there? Just 2. Okay. We're obviously storing the value of sum here. Should I calculate it again? Okay. Okay, it's 36. Let's say this is 36. 3, 8, 9 is 21 and 15. 4 and 7. 21. 17. It will be just 10 and 5. And here it will be 1, 3, 8 and 9. And here it will be 6, 4, 3 and 2. Okay. Now let's say we have a query like L comma R comma X, where we have to update elements in this range to AI mod X. Okay. What can we take the value of X? Let's say also we are storing the maximum value, right? So the maximum value for this will be 9. Let's just use another color for it. Blue will be for maximum value. It will be 9. Maximum value for this will be again 9. Again 9. Array. Okay, sorry. Maximum value will be 9. Even here the maximum value will be 9. It will be 9, 8, 3, 1 and 3. Here the maximum value will be 6, 6, 6, 4, 3, 2 and 3. Okay. So if we have a query like 3, 7 and value of X let's take 5. So I think the propagation is pretty clear, so I'll just I think the propagation is pretty clear, so I'll just move it down here. Like we'll go to these nodes, and right, this is the first node that we visit, 17 one. The max value is 9 and the value of x is 5, so it's definitely less than our max value. Again, I should write the two conditions that we have. The break condition is x is greater than max value, and the propagation condition the propagation condition is x is less than or equal to our max value. So we'll just have to propagate down to both of its child nodes. Now here we have entered a leaf node or a leaf node. So we'll simply update this value. Now 8 mod 5 will give us 3. Its max value will be updated accordingly. 9 will be updated to 4, and so will its max value. Now again, traversing back, we'll check the sum. It will give 8, and also we have to check what the max value is. So we'll compare the max value of both the ranges, and we'll end up getting 4. Now again, propagating up, we'll get 4 plus 8 as 12. This value will be updated by 12, and this max value will be updated by max of 3 and max of 4. So this will again become 4. Now before returning it here, we have to traverse this end also. So we'll traverse from here to here, and what was the range? 3 to 7. So we have to go till here. Here our max value is 6. Okay, first we'll traverse this node. Here our max value is 6 and the value of x is 5. So we have to traverse its children as well. Here our max value is 6 and max value is 4. But since they are leaf nodes, we'll update anyways. And this will be updated to 6 mod 5, which is 1. And this max value will be updated accordingly as 1. This 4 will remain unchanged since it's less than 5. So it's kind of a break statement, but pretty useless because it's at the leaf node. So we'll further update the sum values. Using 1 plus 4 will give us 5. So this 10 will be updated to 5. And the max of 1 and max of 4 will update this max value to 4. Now we have reached this node, and still there is a range of value that we can further propagate to, since this is covering the nodes, the indices 7 and 8. So we can further traverse to this node, but the maximum value here is 3 and the value of x is 5, so it completely follows our break condition. So we'll just stop propagating here and just return the value without propagating further to its children. So that was the break condition. Again, we'll propagate up. The 5 and 5 will give us some 10. The 4 and 3 will result in the maximum value getting updated to 4, and again we'll get here 22, and 4 plus 4 will give 8. This is more or less the approach using segmentary beats. The main difference to notice here was, first of all, we are not just focusing on the range that we are updating for making the decision. Like we are making the decision, right? Either we have to break or propagate, or in lazy propagation we have to put a tag condition. So for checking which condition we have to follow, we don't have to depend only on our range. We have to depend on some of the property of the nodes that we are looking at, of the elements of the nodes we are looking at. For example, here our property was the max element. This is a property that we are looking for. Based on this property and the indices that we are updating together, we'll make the decision of whether we have to break or we have to propagate further down. So this is the basic essence of segmentary beats. I think the approach should be pretty clear by now. Let's just see why the time complexity is not linear per query. Like, you might be thinking something like, if I just take the mod something like mod 1, like of course all the elements will get 0, but you're getting what I'm trying to say, right? If we'll take something mod a value that is even smaller than the minimum value in the array, then all the elements have to be updated. So we'll have to go down to all these leaf nodes, basically traversing the entire tree. And yeah, so this query might take O of n time, but now we'll try to prove by the average time complexity for all the queries will still be logarithmic and not linear. So yeah, just let's move on to the proof of it. So yeah, again there are things that we could notice here. Let's say we have like let's take an array indice. AI is an integer we have, and we are taking AI mod x. Again, we have discussed the two conditions that it falls through. One is where AI will be smaller than x, which will be no change. So we don't have to worry about this case because we are not propagating further down. But if AI is not equal, not less than x, then we have to propagate further down. But we can still notice one thing here. It can be easily proved that if AI is greater than equal to x, then AI mod x will be less than x by 2. No, sorry, less than AI by 2. I think you might have seen this somewhere, or you should be able to prove it easily. Like, if I have to give a basic overview of how it is proved, then like just break it down to two cases where we are taking a number like where x will be less than AI by 2 or x will be greater than equal to AI by 2. In this case, x will we'll take AI by 2 greater than AI by 2. In this case, it will just be AI minus x. And in this case, since x is less than AI by 2, so anything mod x will result in a value which is less than AI by 2. So in both the cases, we'll get a value which is less than or equal, not even equal, less than half of the value that we initially had. Okay. So yeah, we can somehow use this in our proof. Since there is no scope of increasing an element, right? So, and if there is no change, then we are not propagating down. So this no change condition is something that we can completely ignore, or we'll just write it for a formal proof or the formal final time complexity. But this is not something that we should worry about. The main thing that was kind of bothering us above was this propagation condition, because we were propagating down to both the children, and this was the case where we have to update the nodes. So that update condition will be only there when AI is greater than x, and it will reduce the updated element value to less than half of it. So we can say that if all the elements in AI are less than or equal to some value u. Yeah, like the upper bound should be u. Yeah, for I 0 to n, okay, 1 to n. If they are capped at some value u, then each of the element can be updated at most log u times. So it will be order of log u times. This is the first thing that we can notice here. The first thing that we could notice here is if an element is getting changed, it can only be changed at most log u times. There's another thing that we can notice here. Like I should go to the tree. Yeah. For changing a single element, for changing a single node, like, yeah, I have to go down entirely to the leaf node where that element is present and then propagate up. So in the worst case possible, where will it be? Like let's say we are trying to update this single value, 8th value. I have to go down entirely and update it. Yeah. So how can I explain this? Let's just take this example. So I'll draw a small tree here. If an element is getting updated, we have to travel. If this range was getting updated, change the color. Yeah, this range was getting updated. We have to travel extra log n nodes for a single element. Like in the worst case, we have to travel log n nodes for updating an element. Updating one single element, like the number of nodes that we have to travel. How do I frame it? Yeah, so this log n is not the average query that I'm talking about. I'm saying if I have to update a single element, for example this element, then I have to travel log n extra steps. Like a standard segment tree propagation is fine. I am traveling log n queries in a standard segment tree propagation for each query. But this is just extra time that we are propagating down. Even if we get a range that completely fits right here, we still have to propagate down, and that's the issue. For example, this is the range. We could stop here, but since it's getting updated, for each element we have to travel log n extra time for each element. So for changing an element, let me just write it down again. We have to traverse at most or order of log n extra nodes. Like I'll be using this extra a lot of time even when I'll be trying to prove the next question. Like if I have in a normal segment tree propagation, if my traversal just ended here and let's say all these 4 elements are getting updated, yeah, all these 4 elements are getting updated, then for each of these elements we have to travel order of log n extra time. So our traversal count just increased, and but we can still prove it that the average time complexity will still be logarithmic, because here we have seen that we can update a single element at most log u times. So a single update is taking log n time. A single element, worst case, will be log n. And how many times can we update a single element? It's order of log u. Just give me a second. Yeah, I think my screen should be visible. Yeah. So a single update is taking order of log n, and the total number of updates that a single element can go through is order of log u, and there are total number of elements we have. Total number of elements, it's order of n. Okay, so using this we can easily say, even if we are taking the worst case into account, like we are propagating continuously, it can never exceed n log n times log u, order of n log u. It can never exceed it. Like it can not mathematically exceed it. Let me just give a brief of what we have done till now. Our standard segment tree was taking order of q log n, and we have two conditions here: break condition and propagation condition. Our break condition will always follow this for average query, not the all the queries combined, but average query for the break condition will just remain the same as a standard segment tree. The propagation condition will follow this. Even if in the worst case we are propagating continuously, it can never exceed n log n times log u, because an element cannot be updated more than log u times, and each update will take log of n time. So yeah, that's the proof of time complexity for this problem statement. Now I'll not be looking into the codes of this, because I'm assuming you have a good grasp of lazy propagation, and the entire code of this should be pretty close to lazy propagation. Not even lazy propagation, like we are not using tag here, but we are eventually using some extra information, so you have to update or tweak a code the little bit, but it should not be a complex task, so I'm just skipping it. Understanding the code is like very easy. The most difficult part is to understand how this time complexity is actually working, and just accepting that somehow you will end up having an intuition, like as an intuition such as this. Like, this was definitely not so intuitive for me, at least. Let's just look at the second problem statement that we were talking about, which is we have to update the elements to min of ai comma x. Okay. Yeah. Yeah, minimum of A, X. Okay. So, how can we build an intuition for this? We'll still have to store some extra information. We have to store more extra information than we did previously for solving this problem. If you want to try it yourself, then sure, go ahead. I can write the problem statement right here and you can just try it. You have an you have an array size n, and you will be given queries which will be of two forms. First will be update query, where you will be given L, R and X, and for all the elements in the range L to R, you have to update them. AI is equal to minimum of AI and X. Okay. For all I in L to R. And the second will be a sum query, where we have to output the sum of all the elements in this range. This is the problem statement we have. You can, based on the above problem statement, you can definitely try to solve it. If you I don't think so the above problem statement is enough for building an intuition for this. So just let me give some hints. Here you have to store more information. You'll have to store maximum element for a node, the second maximum element. You'll also have to store the count of max element. Yeah. Also, a tag condition will be coming here. So there will be three conditions. A break condition will be there, a tag condition will be there, and a propagation condition will be there. So yeah, you can try solving it by yourself, like building up these conditions where I'll have to break, where I'll just use a tag, where I just have to propagate down to further nodes. Okay. So yeah, again we have storing the max element and the second max elements. So based on that, we'll just try to gather up some information and like try to divide these conditions. Where can I break, where I have to use a tag, and where I have to propagate down further. Okay. Can we skip using the count for second max? Just give me a second. Okay, let's just say we are also keeping a count of the second max element. Okay. Now, there can be three cases. Like, we are storing the max element and second max element. Let's just name them M1 and M2 for any node in the segment tree. Then the cases will be M1 is less than X. Again, if we notice, even if we take the minimum of X and the current values of all the nodes, all the indices present in a node, it will just have no change on that entire segment. So this will be our break condition. The second case will be, or just put an equality here, okay. The second case will be when m2 is less than x, but x is less than m1. Again an equality here. This will be our tag condition. Now how can we develop an intuition for this? Why is this our tag condition? What can we see here? First of all, for the node that we are traversing right now, if x is only smaller than the largest element present among the elements that are present in this node, then only this single value will be affected and the count will remain the same. Okay. Yeah. We have to remove the equality, because if there is an equality, then the max element will become m2 and we'll have to update the second max element as well, so which we cannot predict directly, so it will be a part of our propagation condition. So I'll just remove this equality here. Okay. Yeah. So our second max element will remain the same after this. Our max element will be changed to x, yeah. And the count of max element will remain the same because all of them were changed to x. So yeah, we can directly update the sum. Like if initially we had a sum s, then we can first subtract all the m1 values from it. So it will be minus m1 times c. So we have deleted all the instances of m1 and we have to add this element which is now replacing m1. So x times c. This will be our new sum. So we are easily able to predict the sum and we can even propagate it down to its children. Like take minimum of x and take minimum of x, something like this. Why are we able to do so? Because again, ultimately they are covering the same range. Like the node right here is covering a range which is subset of this node, and similarly this node right here is covering a range which is a subset of this node. So if this particular node has a max value m1, then we can easily say that the max value of this node will either be m1 or a value which is smaller than m1. And the same goes for this node. The max value will be either m1 or some value smaller than m1. Okay, and similarly we can say for the second max that yeah, x has to be greater than second max. Yeah, since there are no two distinct elements in the parent that were greater than x, so there cannot be two distinct elements in the children as well that are greater than x. So we'll either end up for each child, we'll either end up in the break condition where x is greater than all the elements, or we'll end up in a tag condition where x is greater than the second largest element and smaller than the largest element. And again, if it's a break condition, we can ignore propagating downwards or even adding a tag downwards, because there is like no benefit of adding a tag. If all the elements in the parent are smaller than value x, then all the elements in both the children will be smaller than x as well. And if it's a tag condition, again similar to lazy propagation, we'll propagate those values downwards. So yeah, this was a tag condition. Now let's look at the third case where x is smaller than m2. Yeah, this is our propagation condition. Now we cannot predict because we basically don't know what our third largest element is. So I mean, you can involve it, but it will just make up your implementation a bit messy, which is already a bit messier. So yeah, we can just propagate down to both of its children as we did in the mod problem that we solved above, and just keep propagating down until we end up at either a break condition or a tag condition. Again, it's exactly the same way as we did before. We were propagating down until we get a break condition. We were basically waiting for a break condition to occur, and here we are either waiting for a break condition or a tag condition. The complexities of both break and tag condition will be the same because we are not propagating down at a tag condition similar to a lazy propagation technique. We are just putting a tag to both of its children. So yeah, again, our goal will be to prove why this propagation condition is not exceeding the time complexity, and yeah, why the average time complexity for each query will not be linear and rather it would be logarithmic. So we'll be proving it, but first we'll just look at an example of how we are actually using this break condition, tag condition and propagation condition. So let's take an example again. One, 3, 8, 9, 3, 2, 3, 9. Or yeah, it's minimum, so we can take different numbers. 6, 5 here, 5, 6 and 1, 2. Yeah. First, let's say the tree will look something like this. I have to draw a bigger tree. We are storing a lot of information. Okay. I'll just write the values first. 1, 3, 8, 9, 5, 6. I don't know. Mine 35. This will be 21, 14. 4, 17, 11, 3, and again these are the single values. 1, 3, 8, 9, 5, 6 and 1, 2. Now what are the information that we are storing? We're storing the max value. Okay, the max value is 9. Let's just take some convention first. Like I'll denote M1 for the max value. I'll denote M2 for the second max value. Or yeah, even keeping it easier. Yeah. Yeah, okay. M1 will be our max value, M2 will be our second max value. Count 1 will be the occurrences of M1. So occurrences of M1. That's it, right? Yeah. Okay. So I'll store M1, M2, C. This will look something like 9, 8, 1. Here it will be again 9, 8, 1. Here it will be 6, 5, 1. Here 3, 1, 1. 9, 8, 1. 6, 5, 1. 2, 1. 2, 1, 1. Okay. I'm not writing anything here. For the second max here, you can store something like minus infinity. It should work. Now, let's just say, take an easy example for the starters. We are updating this entire range and replacing all the elements of that element and 4. We'll propagate down in this direction. Just change the color. Okay. We'll propagate down in this direction. The entire range fits in, so we'll check for the max and second max. Now 4 is less than second max, so it's a propagation condition. So should I write all the conditions here? I think it's pretty clear. If an element is smaller than second largest element, it will be a propagation condition, so we'll just propagate down to both of the children. Here again, second max element is still greater than our required value 4, so we'll propagate down further, and we have ended up at a leaf node, so we'll just update it directly 4, and using these we'll propagate upwards and update these max, second max, and the number of instances the max value is occurring in that segment. So yeah, for this the triplet will look something like 4, minus infinite, 1, and for this node again it will look something like this. So using this information, we can say for this node 11 for this node 11 our final triplet will look something like 4, minus infinity, 2, completely using these two nodes and traversing upwards. Now we are at this node, and here our max value is 2, which is less than 4, so it's a break condition. Like taking the minimum with 4 and the element itself does not make any change to this entire segment, so we'll just propagate upwards. And yeah, merging these two nodes again, here the max value is 4, second max value, there is no second max value. Here the second max value will be 2, which is max value of this node. So this triplet will be updated to 4, 2, and number of instances of 4, which is taken from here, will be 2. Again we'll propagate upwards. Like 9 and 8 are the max and second max value, so 4 and 2 will not do any change, so it will finally lead to the same max, second max values. Also I forgot to update the sum. Like 4 plus 4 will give 8, 8 plus 3 will give 11, and 11 plus 21 will further give 32. I think it should have been pretty intuitive that we have to update the sum as well. So yeah, I think the tag condition was not covered in this. We have seen how the break condition and the propagation condition works. So for tag condition we can take some example where our minimum value should be somewhere between the maximum value in the range and the second maximum value in the range. So let's say we are not the leaf nodes. Okay, we are updating this segment and we are taking minimum bit 2. Again we'll propagate down. We have come to this node which is completely inside the range 1, 2, which we are updating. So here we'll be checking our max, second max, and tag. So our max is greater than the value that we are taking minimum with, but it's greater than our second max value. So this will be our tag condition. Now how will I update this node now? since only the max value is changing, I'll just stop at this node and update the max value to 2, and the count of max value will still remain the same. So this 3 will be updated to 2, and I can change the sum also, like sum minus is equal to 3 times 1, where 1 is the count of how many max elements were there in this segment, and plus is equals to 2 times 1, 2 being a new element and 1 is again the number of occurrences of that element. So yeah, this will be updated to 1 and our sum will be updated to 3, and we'll propagate this down here, 2 and 2. Like these tags are added to these nodes, these child nodes of the parent, for which tag condition was held true. Okay, and we have already seen why the tag condition works correctly. Like if there's a tag condition on a particular node, then it's impossible for its children to have a propagation condition. So they'll end up having a tag condition themselves or a break condition. So we can use lazy propagation here. Yeah, I think these examples should be enough. If I propagate upwards, again it will lead to 20 and no change in this 9, 8 and 1, and this 20 and 11 will give our final sum value as 31. Okay. Yeah. And answering the sum queries for both the questions, like this question and the previous question, I think those are the easiest part of this lecture. They can be easily done using a standard segment tree. Like we are updating a standard segment tree, right? Only the update query is the one that we have to be worried about. Let's just see how we can prove that this time complexity would not be linear per query. The average time complexity will still be logarithmic per query. We have to prove it. There are many ways to prove it. I'll try to prove it using the way which I felt was the most intuitive among all the proofs. So again, there are many things that we can notice here. Like there are break condition, tag condition and propagation condition. These are just our standard segment tree or our lazy propagation or tag, whatever you want to call it. These will not be traversing extra nodes in the segment tree. Again, I'm using extra nodes which I used in the previous example. Extra nodes are basically, again, I'm just for recalling it, extra nodes are the nodes that we are not supposed to propagate in a standard segment tree. Like if we end up on a node that completely fits in the range that we are trying to update, we are supposed to stop at that node, right? Like if a node is covering elements in the range 3 to 4 and we have to update all the elements from 1 to 8, then we can just stop at 3 to 4 because it completely fits in that range. So yeah, the extra nodes that we are visiting are the nodes apart from these standard nodes that we are visiting. So here no extra nodes are visited, and average query time, again it will be log n if we are not visiting any extra nodes. The query average time complexity of a query or the average number of nodes that we travel per query will be log n, because like height of the segment tree is order of log n. Okay, again we have to worry about this propagation condition. How can we prove it? Again, there are things that we can notice here. Something like Let's just name a variable C, where C is the summation of number of distinct elements in the range L to R. Yeah, in the range L to R, where this L to R is a segment in the segment tree. So basically, for all these nodes that we have here, C is the summation of number of distinct elements per node. Like if there are 8 elements, right? So if all the elements are distinct, its contribution will be 8. If all 4 elements here are distinct, its contribution will be 4. And summation of all this will give us the value C. What can C be at max? Like the maximum value of C. Let's just try to take the contribution of each level. If this is the maximum level that we have, and this is the lowest level. Here we have n nodes, here we have n by 2, n by 4, all the way up to here only one node. So even in the worst case possible, where all the elements are different, from this level we'll get n times 1, because there are n nodes and the number of distinct elements in each node is 1, so we'll get n times 1. From the second last level, if all the elements are distinct in each of the node, then for each node there are 2 distinct elements. So contribution of each node will be 2, and there are n by 2 nodes, which will give us n by 2 times 2. Similarly, n by 4 times 4, all the way up to the height of the tree. And this will give us n log n, because log n is the height of the tree. So C can be order of n log n at max. Summation of different elements in each of the node can be order of n log n at max. This is the first thing that we notice. Apart from this, what we can say, there is a tag condition and propagation condition. Only these 2 conditions are where our elements will get changed. So only the tag condition and propagation condition can affect the value of this C anyhow. So we'll try to see if we recognize a pattern or just something which will help us to finalize time complexity. Okay, let's talk about the tag condition first. The tag condition will appear when our maximum value is less than x, which is greater than our second maximum value. How many values will it affect at max if we are talking about? Like, if we had a child node, let's say it had elements 1 and 2, and another child node which had elements let's just 1 and 4, sorry, and here we have another child which has 1 and 4 and 6, okay, and all the way up to the root of the segment tree. Now this node has 3 distinct elements. again the node above it will have, let's say, k different elements, and so on. The contribution of these two nodes will be 4. But now let's say in this range, in this array yaar okay, in this range I'm taking min of ai comma 3, so this will get updated to 1 comma 3, even though like it will become 1 comma 3, even though the number of distinct elements in this level is still 4. Like the contribution of these two nodes is still 4, but the contribution here, it will be increased. Like it will become 1346 and not 1446. So the number of elements, distinct elements, will be 4. Similarly, if initially it was k, will become k plus 1. Given 3 was not initially present in that node. Okay, I'm talking about the worst case. So in the worst case, our C can be increased by order of log n, where log n is the height of the tree. So basically updating all the nodes right up to the root node, like updating the value of number of distinct elements per node can be at max increased by 1 if we are talking about the tag condition. Only the max value is getting changed, right? So we can definitely not introduce 2 new values at once. If a node is getting updated, only a single value can be increased in the nodes above it at max. So yeah. So this is order of log n. Change in C, okay. Yeah, change in C is order of log n when we are talking about the tag condition. Now let's talk about the propagation condition. Or yeah, if we are talking about the propagation condition, again we have some segment tree. Okay. In the propagation condition, our value x, like we're talking about, is less than the second max element. So it will definitely propagate down to the children. But here we can say that less than or equal to the second max. We'll keep on propagating down to new nodes until we hit a tag condition or a break condition. So how do I frame it? Like if we are changing one element, not changing one element, if we are decreasing C by 1. What do I mean by decreasing C by 1? Is that at least 2 elements which were initially different from each other end up getting the same values. Example, we have 1, 3, 5 and 7. If this is a node, there are 4 distinct values in it. And now if I take minimum with 4, minimum of 4 comma whatever element it is, then it will result in this following segment, and the number of distinct values here is 3. And yeah, so a value of C is decreased, and not just by 1, it's decreased by 2, because these two are eventually breaking down into a single node themselves. So initially that node had two distinct elements, and now there will be only a single element. So yeah, that's why we have even an extra traversal there. So if we had 1 3 5 7 and we are taking minimum with 4, here we have 1 and 3, here we have 5 and 7. This will be our break condition, we won't do anything. And here we have to traverse again deep into 5 and 7. This 5 will be updated to 4, 7 will be updated to 4. Again this 5 will be updated to 4, 7 will be updated to 4, up until here. Like the individual values we are not manipulating, I'm just showing that we have to traverse these many nodes. Yeah, so we can say that decrease C by 1. Yeah. If we have to decrease C, just give me a second. Sorry. Okay, where were we? Yeah. So decreasing C by 1. Okay. It won't be 1. Just give me a second. I think I wrote something wrong. Just verify it once. It's better than writing something has some wrong information. Never mind, I was going in the correct direction. Okay, sorry. Yeah, let's just give a basic overview of whatever we did right now. Like a tag condition will lead to an increase in value of C by order of log n. And for every value change, we have to traverse extra nodes. In the propagation condition. Right. And yeah, we can say each of the extra node that we are traversing. I think this statement should be intuitive. Yeah, I got confused in this one. Each of the extra node that we are traversing, basically merging elements. Like if the max and second max, and then we have the value with which minimum we are taking, then we are basically merging the two values to that minimum value, right? And for that we have to travel some extra nodes. Similarly for each of them we have to travel some extra nodes. That extra nodes will be of order we have to travel down entirely, right? Yeah, worst case those extra nodes will be of order log n. Yeah, this thing just confused me a lot. Okay, sorry. Yeah, so we have two things that we have noticed now. First, the value of C is increasing by at most order of log n. And for changing its value, if we are trying to merge two elements, we still require order of log n, and it will decrease the value of C by order of log n as well. Okay. So for propagation condition, eventually, yeah, we traverse some extra vertices, but yeah, whatever. But we have to keep in mind, right, that this value C cannot be negative. Even there will be some minimum value of C, and it will be the number of nodes in the segment tree. But during our propagation condition, which cannot infinitely occur because there's a limited value of C that we initially have, and we can only increase it by a certain value as well, because only the tag value can lead to the increment of this value C, and which will be at max log n addition of log n value for each query. So even if it was n log n initially, our further scope of increasing it will never exceed q of log n. Like if we decrease it, then increase it, then decrease, increase, even then the overall increment will never exceed this q of log n value, because there are q queries, and in a single query we are not able to increase it by more than log n. So we have it's n log n plus q log n is the total number of, not the total number of vertices, not even the C value, the initial C value that we had plus the total increment that overall we had. Only these are the amount of vertices, or like not the vertices, basically how much can C be manipulated. Like initially it was n log, let's say it was decreased, then increased, then decreased for some time, then increased for some time. That total summation of increment can never exceed q of log n. So the decrement has to be of a similar order, so that C is greater than whatever the minimum value C can be. Like the minimum value of C is 2n or order of n, so it should remain greater than it. So if the increment is bounded, the decrement of C should also be bounded. I think this is pretty clear. I will just say it again. Like the increment in value of C, which we have seen for each query, the tag condition cannot increase C more than order of log n. So overall increment throughout the entire sequence of updates can never cross q times log n. And since C even has a lower bound, so the overall decrement, which is basically the number of extra vertices that we have to cover during the propagation condition, it will never exceed a certain value which will be of the same order. And that proves the time complexity will be bounded by n plus q log n. This time complexity proof, it's a bit confusing, but especially this propagation part. I'll surely try to attach a blog link. I'll surely try to attach some blog link in the description. And even a problem link in the description. You can just read this blog link once just to clarify this proof. I think this was the most confusing part. I did not teach it well. I'm so sorry. It's so hard to explain and frame everything, which in order to make it as simple as possible, I was trying to write everything in a very layman way or a very simple way, and it got me confused at the end. So I think it was definitely my fault. So I'll just attach this blog link and also a problem link, which I think will be very similar to the minimum query problem that we just solved. You can try to code it. You can even try to code the mod value problem that we solved before. And this blog will also contain, I think, the problem links and some other problems that we can solve using segment tree beats, so you can definitely check them out. And the codes are like really simple if you have good grasp of how the code of lazy propagation and just the standard segment tree works. So yeah, that was pretty much it for segment tree beats. Thank you so much.